Hello, Chem 2, and welcome to the second video in Chapter 2, where we're going to focus a little bit more on the periodic table and what information the periodic table can give you. Chapter 2 is atoms, molecules, and ions. From the atom perspective, we're going to spend a little more time about how to use and how to interpret the periodic table. So we've already done the sections. Ooh, made myself bigger. We've already done the sections on nuclear symbols, atomic mass, isotopic abundances, where the Avogadro's number comes into play, that 6.022 times 10 to the 23rd. Well, now we're going to talk about the elements of the periodic table and structural, condensed, and molecular formulas. So we've already done section 3. We're going to do 4 and 5 with this video. So let's get started. So section 4 talks about the periodic table. It's all about the introduction to the periodic table. So let's refresh your memory from Chem 1. The periodic table is laid out as a big table. It's called a periodic table for a reason. It's also periodic because the properties of the elements have a cyclic or periodic nature. Mendeleev laid the periodic table into rows and into columns. Well, the rows was a cycle through a series of chemical characteristics. What he noticed initially was, like every seventh or eighth element had the same types of chemical characteristics. So he'd go 1, 2, 3, 4, 5, 6, 7, 8. And you say, wait a second, 8 looks a lot like 1. So instead of me putting it at 8, I'm going to put it all the way back to 1. 9, 10, 11, 12, and think, whoa, come back around. And he noticed that the columns all had similar chemical characteristics. So he called them groups. And the rows, the times through that cycle, when you talk about physics, the time that a pendulum goes through a cycle, it's called a period. They were called periods. On the periodic table, it's broken into sections. So there are what's called the main group elements, and that's column 1, column 2, column 13, 14, 15, 16, 17, and 18. And in your classroom resources, you have a copy of the periodic table that I created that lays things out pretty nicely. So group 1 and 2, that's where hydrogen is and beryllium is. Those all are the beginning. Those left two columns are the main elements. And then the other side, where 13 on, that's the other part. Those are main group. And in the middle, that's where you have what's called the transition elements. And on the very, very bottom, you have what are called intertransition elements. And on the periodic table also, the lower part of groups 13, 14, 15, one of the terms that are used are post-transition elements. You can also break it down into families, the alkali metals, the alkaline earth metals, and the halogens. So here's an example of the periodic table. Well, let me make my face a little bit smaller so I don't take up so much of the screen. There we go. So there's an example of the periodic table. The first column is where the alkali metals are. The second column is where the alkaline earth metals are. Column 1 and column 2 is your first part of your main body. Starting with 3 to 8, those are also part of the main body elements. So you have the boron family, the carbon family, the nitrogen family, the oxygen family, or other term for it are the chalogens. And you also have the fluorine family, which is the halogens. Chalogens and halogens, that's funny. And then the noble gases. In the middle here are called the transition metals. So if I draw a diagonal line over here, and I look at these elements down here, these are the ones that are called the post-transition elements. And that's because after the transition elements, things get a little weird over in this section because you've got this weird section in between that changes the consistency of the periodic table. So this area on the right-hand side is called the post-transition. And these down here are called the intertransition. The main reason they're called the intertransition is these two rows go right here where this little black bar is. So the periodic table is actually a whole lot wider. It doesn't fit very well on a normal table. So that's why they kind of cut them out and put them down below. But these two slices should be right there where that black line is. Now, Mendeleev was given credit for developing the periodic table. Reality check is he was not the first person to do that. There was But Mendeleev was a blooming genius. I can't go on enough. If you get a chance to look at this video that's on here, that's on the periodic table, it's an amazing video. It talks about how cool Dmitri Mendeleev was and what he did. But he ordered them according to atomic number. He listed the elements according to their atomic number or their mass as he knew it, and he did that cyclicking thing, and he put them in rows where each row had very similar chemical characteristics. And some of the really cool things he did, again, this video can be pretty helpful if you get a chance to watch it, is he had empty spaces, and that's the profound nature of what Dmitri Mendeleev did. It would be the equivalent of you finding a deck of cards and you sorting through it and laying it out and saying, "Oh, you're missing the two of diamonds." How'd you know that? Well, you laid them out in order. You knew they went ace through king, and ace through king on the diamonds was missing a spot. That was where the two goes. You say, "Well, you're missing a two of diamonds." Dmitri Mendeleev did the same thing, but he did it with elements that weren't found in nature at all yet. Yet he still predicted a lot of properties of those elements and nailed them. He did just an amazing job. So again, if you get a chance to watch this video, it's a nicely done video. It's about Dmitri Mendeleev and how he did it. It's a brief, maybe 5 minute long. So how do we read the periodic table? Well, when we look at a cell on a periodic table, that's what each one of the squares is called. It will normally have these 4 pieces of information: a whole number, usually somewhere around the top, a letter or 2, a decimal number, and then, of course, some word. Well, the whole number that's across the top, that whole number across the top is the atomic number. It tells you the number of protons. So that tells me that element neon has 10 protons. The fact that there's a whole number 10 at the top of the cell for neon says that neon has 10 protons. The other numbers are on there is to tell you that, well, just because of the general nature, since protons and electrons are opposite in charge, if we have a neutral atom, the protons and the electrons are going to be the same. So since an atom of nickel has 28 protons because of that number, we know that an atom of nickel has 28 electrons. So we can quantify the number of subatomic particles. Other things on there. You've got metals, nonmetals, and metalloids. Okay? Metals have these 4 properties. They're shiny, they conduct electricity and heat, they're malleable, which means they can be smashed and dented but not shattered into a gajillion pieces, and they're ductile. They're able to be stretched out into a wire. Nonmetals have none of those properties. They're not shiny, they do not conduct electricity or heat, they are not malleable, and they are not ductile. They're not. Semi-metals will have some of the properties. They'll have 1, 2, or 3 of the properties, not all 4, and not 0. So they are semi-metals. If you look on a periodic table, you can see that the periodic table nicely aligns itself according to metals and nonmetals. Metals are always on the left side. Nonmetals are on the right side in the upper right-hand corner, except for hydrogen, which is kind of a weirdo. And then there's a nice dividing line between the two, which are the elements that have kind of properties, the semi-metal properties. So here's an example: silver, nice and shiny; sulfur, which is meh; and then antimony, really shiny, but if you take antimony, it does not. You hit it with a rock or hit it with something hard, it breaks into a gajillion pieces. It's very, 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 very brittle. It looks very shiny. It conducts electricity pretty decently, but it is very, very brittle. It's very, very hard, very brittle. It is not a metal. It looks like a metal, but it's not. So that's section 4. So let's talk about section 5. Section 5 is the beginning of this concept of molecules and ions. Now, those are 2 different concepts. Molecules are substances are covalently bonded together, and ions are charged particles that come together. And the last 2 sections we'll spend on trying to write formulas and names. So let's differentiate between the 2. When two or more atoms come together and they are chemically combined, they form an actual sharing bond. That is going to be a molecule. There's going to be a covalent bond, a very strong force that holds the atoms together. That is a molecule. That substance is going to have what's called a molecular formula. It's going to tell you exactly how much of each one of the atoms are in the structure. So, for instance, water has exactly 2 hydrogens and exactly 1 oxygen within each molecule of water. It's not sometimes 3, sometimes 1. It's exactly, so it's a molecular formula. So here are some examples of structural formulas. They tell you how they're aligned. In water, the oxygen's in the middle and the hydrogens are on the 2 sides. In ammonia, NH3, the nitrogen is in the middle and the hydrogens are on 3 sides. And in this is methane, methane like as a methane gas, that has the carbon in the middle and the 4 hydrogens are on the outside. There's also something called a condensed structural formula. Now, condensed structural formula is used a lot in what's called organic chemistry, where there's a part of the molecule that is very, very repetitive. So this is methyl alcohol. You'll notice that methyl alcohol has this OH on it. That's called the functional group. So that's like the important part. So you'd write that different, and then you say CH3 with an OH. So this H would not be incorporated with these H's because this H here has a structural component to tell you a little bit about the functionality of the molecule. Same thing here with methylamine. This NH3 would be written separately than the CH3. So this molecule would be CH3, NH3, CH3, NH2. The NH2 has a functionality that is different than the CH3. So these H's would not be clumped together in a condensed structural formula. You can also show molecules with what are called space-filling or ball and stick models, both of which give you an idea of the distribution of the electrons, distribution of the atoms. Come to AP Chem, and we'll talk a lot more about molecular geometry of molecules and what that means regarding their general properties. That's kind of a cool concept and a very, very big piece of AP chemistry is molecular geometry and what that means to the chemical and physical properties of the molecules. And then on the flip side of molecules are ions. Ions are charged particles. So when an atom in this situation of sodium loses an electron, now this does not mean sharing an electron, it means losing an electron. When it loses an electron, it becomes a sodium cation and it has a +1 charge because it now has 1 less electron than when it started, which means it has 1 less electron than the protons. So it has a +1 charge. Same thing can be true about what are called anions. If a chlorine atom were to gain 1 more electron, it's going to become a chloride ion with a Cl with a -1 charge. The number of electrons lost by those positive pieces have to be the same as the electrons gained by the negative pieces. And the latter 2 sections will talk a lot more about how that comes to fruition and how we handle formula writing and bonding. So let's look at an example. So scandium is a transition metal. It's usually added to aluminum bikes as an alloy to make it a little lighter but stronger still. I want to know how many protons, neutrons, and electrons are present in a scandium-45 +3 ion. Well, if I look at it, I'm given the nuclear symbol, I'm given the charge, means I can extract out of the nuclear symbol the charge, the atomic number, and the mass number. And all that can give me the protons, neutrons, electrons. So for protons, I just need to know the Z. What was the atomic number? For the neutrons, I have to take the atomic number, the atomic mass, the mass number, and I need to subtract the number of protons to get to my number of neutrons. And then for the electrons, I'm going to take the number of protons minus whatever the charge is. So let's do it. So protons, well, since Z is 21, that's what's down here, the number of protons is 21. The electrons are going to be the number of protons minus the charge. Well, I have 21 protons minus +3 is my charge. So 21 minus 3 is 18. I have 18 electrons. And then for my neutrons, I have to take my mass number and subtract my number of protons. Mass number, which is 45, subtract the number of protons, which is 21. So 45 minus 21 is 24. This substance, this scandium plus 3 isotope, has 21 protons, 18 electrons, and 24 neutrons. Okay, one of the last things we'll do here is we'll talk about the concept of monatomic and polyatomic ions. Monatomic ions are when a single atom is going to gain or lose electrons. Polyatomic ions are a little different. Polyatomic ions are when the atoms are covalently bonded together, but they're covalently bonded together in such a way that they have extra or less number of electrons. So for instance, this ion here is called the hydroxide ion. Hydroxide ion is a oxygen atom covalently bonded to a hydrogen atom, but it needs one extra electron to make that happen. So when it does grab that one extra electron to make it happen, it has an overall -1 charge because overall it has one more electron than it has protons. This is the ammonium ion. When you covalently bond nitrogen, the atom, to hydrogen, the atom, you got one extra electron that you don't really need to make all those bonds happen. So it loses that one electron very readily. Therefore, it becomes a +1 charge. It has one less electron than it started off with. So that's going to be a +1 polyatomic ion. Poly means more than one, has more than one atom in the ion. Ionic compounds tend to form when the pluses and minuses are attracted to one another. And they actually do this in a very organized pattern. And this is what happens with table salt, sodium chloride. Very, very rigid pattern of every other atom is plus or minus, plus or minus, plus or minus in all three directions. And then what happens is when those two pluses and minuses come together, they're attracted together with a very, 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 very strong electrostatic attraction. And that very, very strong electrostatic attraction is called an ionic bond. What happens there is because they're held together so strong with that electrostatic attraction, it takes a lot of energy to break them apart so they have high melting points. However, a lot of them, because of their attraction to water being greater than their attraction to one another, are going to be water soluble. When a ionic compound dissolves in water, it's going to split up into its ions. Because it splits up into its charged particles, now that solution is able to conduct electricity. It has charged particles in it. So ionic compounds, when dissolved in water, conduct electricity. Molecular compounds, when they dissolve in water, do not. Example, I take table salt, which looks a lot like sugar, and I take table salt and I dissolve it in water. That salt water conducts electricity very, very well. However, that sugar water, again, dissolves very, very well because the sugar molecules are strongly attracted to the water molecules, and it breaks apart all the attractions between the other sugar molecules. But that material does not have actual charges, so it does not conduct electricity. When molecular compounds are dissolved in water, when they do, and not very often they do, but when they do dissolve in water, since no ions are formed, they do not conduct electricity. So the term that's used is any solution that conducts electricity is called an electrolyte. If it does not conduct electricity, it is not electrolyte. You've probably heard the word electrolyte before used with like Gatorade, Powerade. That's because Gatorade and Powerade have some ions in it. Fun fact, the original version of Gatorade that was discovered by University of Florida, that's why it's called Gatorade, because that's where it was originally designed, was nothing more than Kool-Aid that had some salt in it. The trainer of that team noticed that all of his players, his clothing, had salt on them, so he knew that they were losing salt. And so what he did was he put salt into the Kool-Aid so that the player, he had to put flavor in it so the players would actually drink it. It wasn't just straight water. And voila, the first version of Gatorade was made. Now, it's a lot more sophisticated now with what salts and what amounts, but that was the first Gatorade, which is simply salted Kool-Aid. Talk about conductivity. You stick a probe into pure water. It does not conduct electricity. You stick a probe into sugar water. It does not conduct electricity. You put it into sodium chloride water or salt water. It does conduct electricity. So last thing, conceptual. If I take sodium nitrate, the compound, which is an ionic compound, and I put it into water, it's going to break into its individual parts. You're going to have the sulfur atoms are going to be connected to the potassium atoms are going to be connected to sodium and NO3. God, I'm having a hard time. NO3 ions, but they're all going to be lumped together. That's what's here. So what they want you to do is look at a similar beaker and say, well, what if I had potassium sulfate? What would that solution look like from a conceptual standpoint? Well, for potassium sulfate, the potassium would be individual because you have two, boom, boom, you have two plus one ions. So there's going to be two separate potassium ions. But the sulfate ion is going to stay together with that form, and it's going to have an overall -2 charge. However, this solution is going to have an overall charge of 0 because for every one sulfate with a -2 charge, there's going to be two separate +1 charges in the solution. The overall charge of the solution is going to be neutral. And that's the end of sections 4 and 5. Just like last time, I'm going to remind you that the homework that's associated with sections 4 and 5 is to do the optional OWL for chapter 2 if you need to. I find it to be very, very helpful, and most kids who have any type of struggles have to bite the bullet and say, you know what, I may need to do a little bit extra work. Do the optional OWL. Do parts of the optional OWL. It'll help you understand from a conceptual standpoint the foundational components of this section. And then the graded OWL is the part that's going to go in the grade book. So the graded OWL are a little more complicated problems, but the foundational optional OWLs are really, really helpful. Just going to tell the quick story. Almost every student who has ever had any level of struggle in Chem 2 comes to a degree of realization somewhere down the road, normally when I make them do the optional OWL, that they're really helpful. So I know it feels like extra work, but I'm going to tell you it really does help. And again, remind you like I did with after the last video, chapter unit 1's test is coming right up after the end of chapter 2. So until the next video, stay safe, stay healthy, get that homework done. Toodles.